programs. I'm just going to do a quick revision of sorts. I have yet to read the semaphore section, and I'll read that as well, but first we'll do a revision. So virtualization, first you have all of this crap that they are putting. So first the introduction, right? So we are using the OSTEP book for this, and it's a shit book because it like really is very slow, but hey, this is the best that we can do. Okay, so what's virtualization? Once again, it's when you run the processes as if like they are the only processes, and the OS does all of this. So you virtualize your CPU, your memory, everything, so that like every process that you're going to run, even threads, they feel the illusion that they are running on a single CPU or a single memory address space. Right? So it takes resources and then converts it to virtual version of the resource. So a virtual machine, for example, is literally just something that takes in physical resources of your system and then converts into a virtual thing on which you can probably run another operating system, right? So sometimes you have this thing called VirtualBox, which people run for Linux and all. So those are virtual machines, which are literally like programs which emulate an operating system. All right. System calls. So an operating system by itself is also called a virtual machine, by the way. The system call is basically like it's basically a function call, but what it does is that it gives the control to the operating system kernel, right? And then it decides what it has to do, right? Whether or not to context switch, what program to switch to, what operations does it want to do, all of those things, right? So to allow the users to to tell the operating system what to do, the OS provides system calls, which is the interface through which a programmer can access. So for example, the easiest example of system call is just read and write operations. So when you take input, maybe like through a Python interface, right? You write input and function. It actually does a system call behind the scene. So a system call is basically just like a bit of like assembly code, which is wrapped with a lot of security checks and all that, right? So you need to be in the kernel mode to execute that code, and so system calls do this thing that they switch to the kernel mode, they execute it, and then they go back, right? The standard library, so C has a standard library, right? So it's basically like a collection of all the things that you would need to run a program, right? So it's like it's going to have input output, it's going to have file management and all of that. Similarly, OS also has a standard library, right? So it has all of these nice utility functions, which is, by the way, all assembly, and it's written down so that the programmer can use that, right, whenever they want to do something correctly. So it handles all the threading and all that stuff by itself. So in earlier days, an operating system would literally just be that, the standard library, right? It's just a bunch of functions at that point. So so standard IO, ring a bell yet? It's a standard library we are referring to. The resource management. So the OS nowadays manages the physical resources as well, right? So it does all of these scheduling things and all of that. Okay, so let's actually get into what an OS is. So in OS is, so first you need to know what a process is, right? So I said that OS virtualizes a CPU so that every process runs as if it has its own CPU, right? So a process is basically any application. So for example, this thing that you are seeing right now, it's Notion. This is an application. This is something which is having a process ID, right? And I think so in Linux you can even see the process IDs somewhere. I've forgotten where to look at for that, but I think it's etc PID something. I don't remember the thing. Yeah, but yeah, so every process has its own virtual address space. It has it gets the CPU, and then it like also has this own process struct, right? So OS is basic. Most of the times OSs are built in C, and so C uses structs. So for every process you have a struct associated with it, right? So yeah. There's also something known as a process table, process struct table. I think it's called the PCB, I think, process control block, if I'm not wrong. So every process has an identifier called a PID, and yeah. So concurrency is when multiple processes are running at the same time, or it could also be like multiple threads are running at the same time, right? So OS does not want the processes to intermingle with their address spaces, and so you don't really have to worry about concurrency all that much. But when you have threads, they have the same address spaces, so you do have to worry a lot. And as well, logs and all these things come in, but we won't talk about that right now. So threads have the same memory spaces, processes don't. So when I say same memory space, I'm run this screen copy thing now because I need to write something. It's gonna take some time, by the way. Right. Not even sure if whether or not this is actually going to run. Let's hope it does. Oh, come on, screen copy. Where are you? It's not running, is it? Screen copy. Run. Why aren't you running? And it's connected to it, it's just not allowing it seems. It's file transfer. Maybe I have to change the USB debugging options. Shit, I'll have to change the settings for that. So I'm just trying to mirror my phone's screen so that I can write stuff. I hate what's happening. So developer options. It's not having it, right? Yeah. So how do you enable developer options? You go to the info software. Oh, I do have to. That was so stupid. So USB debugging, where is it? It was turned off, that's why. Yes, always allow from this computer. Cool. Now I don't want this for file transfer, I want this for, I don't know, charging my phone. Okay. Now I can run screen copy. Sometimes these things happen, like these will happen all the time. Here's what I was saying. So you have a process, right? Okay, so you have your full like memory, like this is a block and every column will be like a continuous amount of space. So what's going to happen is every process has its own address space. So this is like for process A and this thing is for process B. And address space is basically just a heap, stack and code segment. So you have the code segment over here, which is also called a text segment. It has all of the static variables defined, all the things which are in the program, right? All the instructions themselves and a bunch of other things. Then you have the stack. The stack, I should write it at the very top itself. So this is your text. Then you have the, so I don't remember how the stack grows. I think this is your heap, like heap grows like this, and then I don't know, it could be anything, it could literally be anything, it does not really matter. I think the stack is the one which grows opposite and heap grows downwards. So text segment does not grow at all. This is probably your heap, right? So these are higher valued addresses, and this is your stack, it's growing upwards, right? So whenever you have a stack pointer, what you do is you do stack pointer, I think it's minus equal to, what the hell, I have forgotten about it, huh? Wow, well that was unexpected. Shit, I don't remember how the virtual address space works. This is bad. Shame on me, and this isn't supposed to be happening. It's probably there somewhere in the virtualization. So there's scheduling, relocation, segmentation. I think this is what I was looking for. Okay. Base and bound approach is wasteful. Yeah, okay, so these are our three main segments, have separate base and bound registers, explicit addressing. Okay, cool. Yeah, so grows positive, right? So the code segment grows positive, the heap segment grows positive, and the stack grows negative, right? The stack grows backward basically. Yeah, so if I remember correctly, then the way this actually works is that this is your stack, right? This is your heap. So you'll already have like a bunch of memory associated for the dynamic allocation thing, and so whenever you do a function call, you will have a stack pointer which throws all of this, and then it goes upward. The heap goes downward. Pretty obvious, right? Yeah, I think so. Hey, just to be sure, I should probably like figure it out by searching. So I'm gonna say code stack and heap, and just go to images. Yeah, so this, okay, so this is a completely bad background. Because what's actually happening is that the text is at the bottom. I have no idea where the text is at the bottom. It really doesn't matter because it will be segmented anyway, so it shouldn't really matter. But apparently what's happening is that your code segment is this is your code segment, this is heap, and this is your stack, and this is like uninitialized space which will initialize as you do malloc and a lot of function calls. So your stack like consumes more and more space whenever you create a stack frame, and then your heap gives you like a heap pointer. So yeah, so in reality this isn't how it quite works. You have these things called pages. So instead what happens is like you actually have this going on. So your stack is just this is actually very weird. Like it should be, so grows backward is, so it grows positive, right? So your code and heap are supposed to grow positive. They are not growing positive. Why does the stack grow backward? I mean, this should be, a growth direction. Something weird is happening. The stack is not supposed to be growing backward. Come on. But okay, this is how they do it, huh? Apparently this direction is positive. That's weird. Oh, okay, this is a low address and this is a, so this should be 0, this should be like some 1000 thing, I don't know. That makes more sense. Okay, so it grows like this, and yes, the stack does grow backwards. So you do stack pointer minus, and yeah, so you decrement a stack pointer, and that gives you a like extra space for a new variable. So whenever you do a what is it called, a prologue and a epilogue, right? Whenever you have to store your saved registers and all of that stuff, you basically decrement your stack rather than incrementing it, which is messed up, but that's just how it is because stack goes backwards. Sure. So yeah, this oh wow, these people are even more messed up. What's happening over here? They have reversed it somehow. No idea what's going on. Heap isn't supposed to be. I'm just going to refer to this thing and to this thing. Okay, this is, I don't know what's going on. So now that we know how does the memory allocation thing works, so what's happening is that there's, for every process there's a base and bound register, right? So the base is like the starting address where your virtual memory starts. The bound is basically like how big is your memory. So if you're trying to access something which is out of bounds, right? So the memory location minus the base is more than the bound, then it's just going to throw an error. You'll be like saying this is a restricted section, you cannot address that, right? So you're going to have a fault basically. Yeah, and sometimes it's called a segmentation fault because apparently C was built in a time when segmentation was the go-to method for virtual addresses, but now it's not. So for segmentation, you're supposed to have like base bound registers for each of these segments, all 3 of them. You can even have more segments than that, but mostly it's just 3. And for each of them, you have the base bound registers. You also have the growth direction, etc. So yeah, take all of that in. Now this is like hardware support, by the way. All right, so this isn't really required anymore. I'm gonna go back to this thing. So this is pretty high level stuff. You don't really need to know all of that. This is what happens for the memory. It's actually pretty easy, like virtualizing pretty easy, right? For the CPU, it's slightly complicated. So for the CPU, what happens is there's a thing called context switching. So after every some delta t, right, so delta t time is called a time slice, you have a timer interrupt go on, and what a timer interrupt does is that it forcefully takes away the CPU from whatever it's running right now, and then gives the CPU to the OS, and the OS decides which process to run next, right? And so because of that, you have scheduling policies and all of that, so you have to come up with all of that so that it's efficient, it's fair, etc. Sure. So once again, a thread is basically a function that is running alongside the main program, and all of these share the same address space. Processes do not share the same address space. Both threads and processes, you use them for context switching, right? So you basically, but a thread is something that is slightly lower level than a process, right? So it's something like you have an application, your application has a bunch of processes, so it's like process A, process B, process C. The process A thing might have a bunch of threads, so it's going to be like thread A1, thread A2, etc. And then both of these things share the same virtual address space. So the virtual address space is for the process, right? Both of these share the same virtual address space as the process A. Now you can duplicate a process by calling a fork and all of that, but then again, like when you want to duplicate a process, it's going to be like, why do it, right? Just run the application like once again. You don't need to duplicate it. But yeah, so when you duplicate a process, since we already segmented our address space, right? So what's going to happen is that the code section is either it's like all copied, and then you create a new virtual address space which is like a copy of this one as a complete duplicate, or you share the code segment, because you know that the code segment is not going to be modified, so it's okay. So with segmentation you can do that, and you want to do this because you want your free list, which is by the way what the OS uses to make sure that the memory allocation is done correctly. You want your free list to be sane, right? There should not be, it should be compact basically. There should not be a lot of holes everywhere. So this fragmentation thing that happens, you don't want that to happen, because it sucks basically. It's not let you allocate more memory, right? So threads, by the way, don't have atomicity of instructions. So whenever you do, like, let's say something like x plus equal to 1, that's a C instruction that you're gonna run, right? What actually happens is that x is something that's stored in the address space, so it will be like, I don't know, something that the compiler recognizes, right? Maybe it's like 0x1111, some address. Let's call it address A. So what's going to happen is, first will happen is like you will have a load instruction, and it will like maybe use the register T1. Shit, I've forgotten the syntax. I think this was the syntax, and then maybe this address is stored somewhere, so like the compiler knows where the address is, so like, okay, just put the address versus like just load immediate or something. I don't remember the thing, but it will be like load immediate, some register, and then the address. So this address might be like 0x111, whatever. It will load this, then and it will increment it. So it will be like add immediate to T1, you just add 1, right? And yeah, so this is going to be add immediate T1 and 1, by the way. Yeah, and then it will store back, so store immediate. Now I don't know if store immediate is a proper instruction, whatever. So it'll just be like store whatever the register value is back to the address that you took it from. So like you do a load process store sort of thing every single time you have to run this. So these instructions, all of them not run one after the other necessarily, because it could be that a process, so a thread 1 is running this instruction, and then somehow a timer interrupt goes on, so like the thread 2 starts, and now thread 2 is loaded this instruction, right? And then it does this thing. So okay, so let's say thread 1 is running the program, and it has gone till this point, right? It has loaded the thing and it has added something to it. Yeah, but it hasn't stored anything yet. Okay, 2 jumps and does the same thing, loads and it adds. haven't stored yet. And now what happens is that you go back to process A, okay, or don't go back. Process B runs the whole thing, suppose, and then you also store the thing, right? And then you go back and then process A stores, because it also has to do the same 3 instructions. So what happened is, although you should have incremented this thing twice, since 2 workers are running, and then both of them incremented by 1, so it should increment 2 times. What actually ends up happening is you only incremented 1 time, so it's weird, right? That's a problem. So this is something known as a critical section, which is a section that you do not want other threads to be working on while one thread is working on it. And so to ensure that something like does not happen, what you do is you make it atomic forcefully. You lock the thing. So you'll do something like, I don't know, pthread mutex. So mutex is basically something that allows you mutual exclusion, and you'll be like some lock. Yeah, and then you'll lock the thing. So I don't remember the syntax for it. I think it's just pthread lock or mutex lock. What was it? I don't remember the thing, but you lock the thing somehow. So let's just call this thing as mute. M is okay, and then you'll just be like lock this thing somehow, lock, and then unlock. And this is not the syntax, by the way. The syntax is a bit more complicated, but yeah. So this is essentially what you want to do. You lock, and then unlock the thing. So like if you have 2 threads which are running at the same time, so both of them won't be able to access the critical section at the same time, and that's a good thing. So your locks can actually also be like, so these are variables, by the way. These can also be static variables, which I like to call as global variables. So they will be like defined before your main point is even starting, and so you can have the different threads sharing the same locks, right? And only one of them can actually lock the thing. The one who acquires the lock is the one who's going to run its critical section, and then another process will be able to run that critical section for a while. Obviously, you can still do context switching, because that's what OS does, right? Like it's not just this one application which is running, which has a lock system built in. A bunch of other applications are there as well, so it can still do context switching, but no thread will be allowed access to a locked segment, to a locked section, right? And this is the stuff that programmers have to worry about. Okay, so threads don't have atomicity of instructions. Users want the data to be saved persistently to non-volatile memory, which is usually treated as an I/O device, right? So your disk is apparently an I/O device as far as the computer system goes, because it has a port. Everything that has a port number is an I/O device. So to help this, OS has just a file system on disk, right? So file is basically like virtualization of the disk. So you virtualize your CPU, your RAM. RAM is what we use for virtual addresses, by the way. This is what we use for running the programs. And then you have the I/O thing, right? You have disks and all of these different, like you have a printer, for example. So you also want to virtualize that. And so the last one, I don't know how it does it. I haven't read to that point. But the first 2 I kind of have an idea. File system does the opposite of privatization, right? So the thread wants to do privatization, like run the program as if they cannot communicate. File is basically something that 2 people should be able to share, and there should be concurrency and everything. And I don't know much, but it does the exact opposite of privatization, as it enables it to be run by a bunch of things while there's sharing of information. Because if you just run through programs normally without any of that happening, they'll just like they will have this read after write dependency problem, and so what's gonna happen, and like write after write, and all sorts of dependency problems. So we don't want that to happen. And so what we want to happen is that the processes should be able to communicate with each other, and this is something known as a producer consumer problem, which we'll learn eventually. But yeah, it's more complicated than that, but it's a bit like it. So system calls for file management, open, write, close. Same in Python, same in C. Okay, most file systems use protocols like journaling, copy on write, to avoid system failures while writing, which I have no idea about. I haven't read till that point. So what does the OS do? It virtualization for processes, it handles concurrency, and it stores persistently. All right, so that's all about what an OS looks like. Let's get into what an OS does. So time sharing is basically like multiple things sharing CPU time. So there's memory sharing and then there's time sharing. So for example, running a process A for 1 second, B for 2 seconds, C for 1 second, and then A again, and so on. This is like giving illusion of the processes that they all are being run, although we know that at one time only one process is being run. So sometimes this is what your brain does as well, right? So like you're running, literally you are like walking, say. So one muscle has to go first, the other muscle has to go after that, etc. So this whole thing, it's not you at the same time you're also like calling somebody and talking on a phone, all of that. Like the reason you can do all of this multitasking is because your brain is a bit like an OS. It runs one thing for a time, the other thing for a time, and so on. So yes, you can do multiple things at the same time apparently, but really you're not doing any one thing as fast as you could, right? And much of it has to do with the fact that your legs moving and all of these things, these are a bit like IO operations. Your brain does not really have all that much of control on when it's gonna hit back on the ground, right? So it just sends a signal, it waits for it, while it's waiting for it, it'll do something else. So it continuously sends signal. And it just so happens like your brain is a bit more like a neural network rather than an OS. So it can in fact multitask. It can do a bunch of parallel processing things, and a CPU cannot. So you are inherently faster than a computer, which is I think something you're proud of. Like you have a parallel processing thing built in, and the computer does not. But you know, whatever. So yeah, since the computer is kind of dumb and limited, we need a lot of policies to make the mechanisms faster, right? So these are the mechanisms. All of this bound-based register stuff, all of the context switching things, mechanisms. Now we need policies, which is where scheduling comes in. Okay, by the way, what's an address space? I think we talked about that already. So you already had this. I don't know why okay, here the thing is opposite, that's why I got confused. So code, then heap, and stack. So stack goes backward, heap and code go down. Down is higher. Yeah, cool. So this is just the program in the memory, because you have to store the program in a file so that you can run it later on. What happens is, so this is actually stored as like bytes. So what happens is there's some program which takes this program and then puts it in the RAM, and then the CPU comes in, and like this becomes a process. So every process has its ID and it has a process struct which describes the process, and then all of this combined is the process control block. So the heap is small, it's basically empty at first, but then repeated usage of malloc, and this causes the OS to come in, it increases the size of the heap, etc. So when you do a malloc, it's not just malloc which is happening, there's a lot going on over there. There's a thing called memory allocation, which we'll discuss later. So similarly, free will make the OS reduce the thing, right? It reduces frees up the memory. And this free up memory thing, there's a thing called free list which OS continuously maintains, and so there's a lot that we have to talk about. Process, this is important because this is something that's going to come in that quiz. So every process can only have 5 states. Either it just started, it has been killed, that's one state. So where's my note? Yeah, so it has just started, or maybe it has been killed, or maybe it's running, because you start and you run, obviously. Maybe it's waiting, it's one possibility, right? It's waiting. Yeah, so it's waiting for an IO operation particularly. So it's either running, it's waiting, or okay, I know what this other thing is. It's basically like the OS put it on wait, right? Like it's ready, or it's actually ready. Basically, ready is the name for this node, right? So you can go from run to ready, ready to run, right? All of that, and then you can do ready to wait and wait to run, and yeah, you can obviously go from opposite as well. All this can happen. All of this is a possibility. And then, so once a process is ready, you can probably just kill it straight up. So killing a process actually needs it to be in the ready state. You cannot just kill a process while it's in the running state, because it does not make any sense. You cannot remove it from the PCB while it's running, because you have to run instructions to remove it, which are only there for the OS to do. So you need to go to the kernel mode. To go to the kernel mode, you have to make it ready. And that's how it works. Wait is a very special thing. Wait is basically when you're waiting for some other event to take place. So this could be a lock. You're maybe waiting for a lock to be released so that you can acquire it in the critical section. This could be an IO operation, which once again leads to locks. Or maybe you're just like, I don't know, something has put you in a waiting state. Just maybe you yourself did that. This will happen. This is a possibility. Maybe there's like a conditional variable which you are waiting for. So whatever reason, you are in a waiting state. So process states: running, ready, blocked. But then again, there's also the start and kill thing, which you really do have to care about. But yeah, so when a ready thing goes to a running state, it's scheduled, otherwise it's descheduled. And when something is running and then like it starts to wait for an IO operation, it's in the block. You can't go from ready to block, by the way, because you literally have to run the process so that it like becomes blocked. And we shouldn't call it blocked, we should call it waiting. I don't know why they're calling it blocked, but okay. So IO, when you are waiting for an IO thing to happen, you basically do a system call. So you go in a waiting state, and then from a waiting state you go to the ready state, right, when the IO thing is done. Yeah, so that's process states. So a process list is this, I think that is it, right? Yeah, so a process list is a list of ready processes that the OS keeps. All right, so that's a process list, keep that in mind. But okay, it's kind of wrong. It's more like queue. Sometimes it's a multi-level queue, in fact, as you will see. So the saved registers form the register context of the process. Thread is more like it. Yeah, okay, I said it's thread because even threads have like different what do we call it? Machine states. Yes, so at a virtual machine, when you're going to run a virtual machine, you'll see there's a thing called save the machine state. What it means is that whenever you will restart the virtual machine, it will start with the exact same state that you left this whole thing on. And that's interesting, isn't it? It literally like takes in whatever state the CPU is in, or CPUs are in, and then it stores it somewhere. That's all it does. It's literally all it does, because the memory and all of that stuff, that's already there. Right? You just have to store the virtual memory somehow. So it does all of that. It stores it on a disk, whatever is in the RAM, it stores it on a disk, and whatever is in the the CPU, it stores that on the disk as well. So yeah. So right, so for every thread, your machine state is stored in the process struct, by the way. When a process is just created, it's in the initial, right, it's not called start, it's called the initial state. And this is a dead state, most likely. So when a process has exited but hasn't cleaned up the memory, it's in the final state. So it's not even killed, it could just be that this thing just got completed, so it's sent to the final state. So when the process is in the final state, all that you have to do is that just to remove all the traces that this process ever existed from the RAM, and good to go. Yeah, So this is useful because now a parent process can examine whether this process has completed or not. If it has completed, it can delete the process. So yeah. Well, if it's completed, then the OS itself kind of deletes it, but whatever. Right. Cool. So that's abstraction. The process API. So fork creates another process. Wait is, so fork also returns the PID, by the way. Right. So wait is a bit like the join thing that you have for threads. So it waits for the child process to finish, and then execution of the parent is continued. The execute runs another compiled program. So this is a bit like the eval thing, right? Yeah, so it does not create another process, it just changes everything. It just changes the CPU state, just like that. So it's a jump condition basically, and it does not have a return. So when you say like execute execution file, it will literally like kill the program and just start running whatever is in the execution file. So just be wary when you use this execute command. First make a process, then try to execute something that's in some other like some other program, right? So that you know it actually works. So this is using the file system, by the way, right? So already a lot is going on when you call execute. Like you are in some other process which was probably called created using fork, because so like if your PID is 0, right, that's what fork does. So then if it was like that your PID is 0, then you'll execute something else. That's basically what we're trying to do, trying to create two processes, both of them being different. So then it will just basically jump to whatever process you want to do, but first it will have to load the stuff from that file. So it's a slow thing, right? So creating processes, it's slow. Creating threads is fast, because for threads you literally just have to write functions and then give the function pointer and it creates a thread. Okay, let's talk about limited direct execution, LDE. Yeah, so this is basically baby proofing our computer. So like let's say there's a stupid programmer who wrote a while loop which will never terminate, right? An infinite while, and you don't have an OS, and you're just running that program, and there are a bunch of other programs which are waiting to be run, and you're expecting this program to run, and then it will halt, and then once it has halted you can run some other program. So whether or not you want this program to keep on running is a tough decision, isn't it? In fact, it's so tough that it's impossible. This is called the halting problem, right? Without an OS, your device is literally just a Turing machine, and on Turing machines you cannot figure out whether or not some other program that you have made, right? So the universal Turing machine is what you are referring to when you say computer. So you do not know whether or not some application is going to halt, and that's a dangerous situation, because if you don't know whether or not it's going to halt, it can literally just keep on running, and then you'll expect it to halt at some point. So it's a bad situation. This is where OS comes in, because if something keeps on running for a lot of time, the OS can jump in and say that we'll give you low priority because you just aren't finishing, right? You are a slow shitty process, so we'll give the fast processes a bit more time. So basically a process is fast by the OS's standards when it keeps giving up the CPU to the OS, right? Something which continuously like does some sort of IO operation or system call or whatever, and then it returns something to the OS. And these processes are very manageable by the OS because the OS gets control after a while, right? Otherwise, what the OS has to do is it has to kill the process, right? Yeah, so there will be like some sort of a timer interrupt which will kill a process if it's running for too long. So we don't want something like that to happen. Instead, what we want to happen is the OS will take away the control. It won't kill the process. It will make the process go in a ready state, and then it will run some other process. So that's what a multi-level feedback queue thing does. And all of that is built on the round robin algorithm. So this is something that people use for fairness, EQ1 fairness particularly, but whatever, let's not talk about that. Mm, right, so what's the timeline for a timer interrupt? Save the registers into kernel stack, so hardware does this automatically. Like whenever you're going to context switch, the first thing that happens is all the registers are somehow stored, right? So every process has its own kernel stack, by the way. Yeah. Then you activate the kernel mode and you jump to the target. So like you jump to the trap handler. So like if you have a system call, then you wanna jump to whatever IO operation is going on. So you'll do that. So when it's a timer interrupt, you'll just straight up jump to whatever is the code written for the timer interrupt. So you'll jump to that trap handler and we call the switch routine, right? That's what the timer interrupt tells the OS to do. And OS is literally just, you know, all of these programs that you written for different interrupts. It just so happens that the timer interrupt is the most important one. So basically it preempts the process and then it handles the control to OS. When I say OS, it's just some program. It's just some program, alright, which is going to always be in the RAM. Right? It's the first thing that is loaded. So it saves the register into the process structure. So remember, you have already saved these things into the kernel stack. Now it uses this thing, which is in the kernel stack, and it saves it into the process structure. And this is something which is handled by the OS. So like OS is, think of it as a C program, right? So if you have a C program, you literally have things called structs. So these things are stored in the process struct. Then you will load register from the process struct, okay, that you want to continue, especially done by the OS. So you are switching, by the way, to some other thing. So what's going to happen is you will load some other processes struct into the kernel stack, right? So you switch to the kernel stack of that process, basically, and then you return from the trap into the other process. So just to reiterate, what happened is when you were exiting, you stored all the registers into the address, so inside the address space that the OS assigned to the process, right? Then the OS stored once again all of those registers into a process struct. Then it switched to the process struct of something else, all right, and then it loaded all of that into the kernel stack of that process, and then it just continued, right? It once again like used all of those variables that you had stored to the kernel stack, and then it continued that. Yeah, that's what happens. Cool. And you so store the registers of the other processes from it. Let's start with the CPU hardware does something. Sure. So you just restore registers of the process from the kernel stack to the CPU. Well, that's not something that the OS does, in fact, because the moment that you start the process, the other process that is, it will just store everything from the kernel stack to the the CPU, right? And then you activate the user mode, right? Because this was the system, this was basically your context switching thing. That's why the OS was there, right? So inside the kernel mode you could context switch, right? When you're in the kernel mode, you can jump to a trap handler, you can save the registers into this thing called process struct, which you cannot use if you're not the OS, because remember, you're not allowed to execute, so use things which are in somebody else's address space, and this is in the kernel's address space, right? So you save the register to the process struct, which is in the kernel, then you load the register from the process struct that you want to continue, switch to that. So you already have the idea of that. Switch to the kernel stack of that process. So it's somewhere, I don't know where it is. It has probably already like stored the address of that. So now you're switching to the other process, and you do a return from trap sort of thing, right? So this thing, jump to trap handler and return from trap, these are jump instructions, by the way. Yeah. So all the while you are in the kernel mode. So when you return from the trap, it just does all of this. Like when you say hardware does this, these are in the end instructions, by the way. So restore the registers of other processes, right? And then so yeah, so the hardware does this all automatically, and then activate the user mode. So the address of the kernel stack, that will be like stored in the process struct most likely. you jump to the program part of this new process, which is also stored in the kernel stack, because program part is also just a register, right? Yeah, so then you can just keep on doing the execution. So I'm gonna write all this down. So first thing you do, so like you have a process, you want to context switch. There's a timer interrupt, so a timer goes off, which we call a tick, by the way. So a tick happens, then the first thing that should happen is that all of the stuff that you were working on, your machine state, is stored in the kernel stack. So CPU registers are stored into the kernel stack of A. So you were running A, by the way, and then some tick happened, and then this is what happened. Then after that, what's going to happen is you'll take stuff from the kernel stack, to the process struct. Of A, alright. Then you know where to switch to, right? So you have some scheduling policy, or maybe even A itself is telling you where does it want to switch to. So you decide decide B, sorry. So this is the most important thing that the OS does. It decides what to run. Then it takes the process struct. So by the way, process struct would already be updated. So it's not like a lot would go wrong if you did not do this step, but it takes the process struct of B, and then it puts this stuff in the kernel stack of B. Then once again, just hardware does this automatically. You go from the kernel stack thing to the CPU, right? So you store all of these registers. So this is basically like a return from trap handler. So this stuff, like you do not want this to be done using instructions. You want this to be done by itself. There should just be some address which you have to specify. Hardware, by the way, just know where to keep all of this, and then based on that address, everything will be stored in some particular location. All right. So for whatever the kernel stack of A is, it will just be stored over there, and then you'll just have the trap handler. All right. So this will just be the trap handler. So you do all of this. This is something that the OS does, and this is a return from trap handler now. Return from trap. And now once again, hardware does this. So what hardware does is it takes the kernel stack of B and then puts all of this into the machine. So puts all of this in the CPU registers. Right? And by this point, you have exited the kernel mode. Yeah. And then you just jump to the program counter. So this, by the way, is it's like an instruction set. This is also an instruction set, and this is something that the hardware does. This is something that the hardware does. Okay. And then you just jump to the program counter, and then you can go back to like normal execution. Sure. So this is what a system call goes like. Save registers to the kernel stack. Switch to the kernel mode. So when you save this, the kernel stack, you do all of this. At the same time, you are also gonna switch to the kernel mode. So this is some sort of interrupt, right? So when the tick happens, you have hardware things going on. At the same time, you are also jumping to some handler. So this is happening in a trap handler, that you're also switching to kernel mode simultaneously. There's some instruction which doesn't. Run the call. So this is basically the call. All of this. In fact, so once the trap handler runs, then you do all of this stuff. This is just the context switching. This is the call mainly. You do a return from the trap, right? So maybe this was a bad thing, that's why we are calling it trap. And then you restore the registers. So this is once again some sort of instruction set which runs, and then it probably has some special instruction which makes the hardware do whatever this thing is. So you have the PID of P with you, right? So just maybe like put all of this in some register, and then you do some instruction and it does all of this automatically. It like goes from the kernel stack to the CPU. So remember, your program counter is actually like stored in some register, right? So when you are restoring registers, even your program counter is restored. So you can straight up just, you don't even need to jump to the program counter. You literally are at the program counter at that point. And that's why hardware is doing all of this and not instructions, because when you are running instructions to do all of this, yeah, like your registers are changing. So that's a problem, isn't it? You don't want your registers to change while this is happening, right? So the program counter being updated is the last thing that should happen. All of this is going to happen by the hardware. Your restoring of registers and your saving of the registers is going to happen by the hardware. Yep, 7% is on kernel stack. So this is basically where the context switch happens. This is the interrupt handler. This is once again an interrupt handler. So this is what we are calling switch basically. You jump to the trap handler, you do switching, you do a return from the trap handler into some other process, you restore the registers, you activate user mode. So yeah, so like you're restoring registers, right? So just before restoring the program counter, like jumping to that, so the program counter is like not updated here particularly, so hardware does this automatically. So you do update all of the other stuff, all of the other registers, but you, before doing all of that, you first activate the user mode and then you just jump to the program counter. So user mode, and you jump to the program counter. True. So you go into the kernel mode once you have saved the registers. So this once again does not count for the program counter at all. So save the registers into kernel stack, and then you want to activate the kernel mode. Then you're going to jump to the trap handler, right? Yeah. So whenever you have this tick, it goes to some piece of code which does all of this. It stores stuff from the CPU to the registers. Your program counter is now different at this point, so it also actually has to store that. And so yeah. Alright, so that's what an OS does. So what about the interrupts while you are in kernel mode? And that's a messed up thing going on. This is weird. But the thing is, you don't really have to worry all that much, because remember, OS is also technically just a program. So even when you are context switching and you get an interrupt, it's all fine. It isn't such a big deal to worry about, because the same stuff will happen again. So it's okay. Like your OS is a process at this point, so it's okay, right? The one problem which you kind of should be worried about is like it's already doing something. So like what happens to that? And it turns out, well, you have to store it. You have to store it in some stack, and then you do another function call. So either you can just disable the interrupt during system call and then processing an interrupt, such as a time interrupt, or you can do locking, which like completely avoids the situation, because then nothing else will be able to do this, right? So if you're gonna like make another instance of the OS, which is a weird thing going on, but yeah, then you probably want to lock this concurrent, this critical section, because something is already going on, so you don't want that to hamper with this. Alright, so that's LDE. Let's go to scheduling, the main thing. So I'm just gonna tell all of this like just from memory. So what's the turn on off time? Let's say that this is your timeline. Your process A starts here. This is when A starts, and this is where A ends. A lot of things happen basically between that. One, your A would be running like this, like over here it's running, over here it's running, over here it's running. In these sections it's not running, it's just something weird is happening. B is running, right? So B is running in these sections. So what's the turnaround time? The turnaround time is basically like whatever A end is that time minus A start. That's your turnaround time. What's the response time? So like B start and B end are these things, but B, although it started here, the first time it was ready is over here, right? So this is B ready, and this may be A ready, I don't know. So the response time for B would just be, or let's just say A would just be A start minus A ready. So the amount of time you have to wait before you get A response is basically your response time. And you can think of A as running in sections, so then you could have an average response time by that analogy, but let's not think about it in too much of a deeper level. Just think of response time as like how much do you have to wait before you start the process. So that's the response time. So it's the amount of time that the job has to wait before getting a response. So it's just first run time minus arrival time. That's it. So what I'm saying is ready time is arrival time. Alright, so let's get to the algorithms. So first, the very simple algorithm is first in first out. That you get a process A, right? It arrives over here, and then you just straight up start doing it. You don't really wait for anything. You could have some other process C running over there or whatever. Maybe you'll wait for that. Okay, so you'll wait for that, and then so at the same start time you'll just start doing it, right? So A will maybe like go till this point, and B has arrived at this point, but you won't do it. You won't do B till that point. Instead you'll start B at this. So here it's A and this is B. So this is just first in first out. Pretty obvious like what's going on. This is really bad for turnaround time, as you can see, and for response time as well, because yeah, it just is. The start time for B and then the end time is over here. Wait, shit, something is weird. Oh yeah, what's the arrival time again? Oh, okay, it's not the A start thing, it's actually the A ready thing. Shit, kind of forgot that. So yeah, that's what turnaround time is, including the non-active CPU cycles at the time the OS is running a different job. Finishing minus the time of arrival, that's what turnaround time is, right? So this is A start minus, so A end minus A read. This is a turnaround, this is response. Alright, cool. So this is really bad for the turnaround time, because as you can see that, okay, for A it was pretty nice, like it turned out as fast as it could, but for B it turned around much later after it arrived, right? It arrived over here and it turned around over here. That's a bad thing. So this is particularly bad when you have B being a short job. If B wasn't such a big job, if it was just a short job, you would want B to be the first priority, like you want to complete it and then continue with A, right? Like let's say you have two projects, one of them is a shorter one, right? You're already doing project A, which is a long semester long project, and then project B is just like it takes 2 days, but you don't do like project B at all till you're done with project A. That's a stupid thing to do. You want project B to be done first because it's short, and that's where shortest job first comes. So you do whatever is the shortest job first. That's the same thing to do, obviously, so that your turnaround time improves. And this is very easy to prove that it's better. Like if you have a process A and a B and both are gonna run at sometimes, it's just always better to run process B before A if B happens to be shorter. Now this only works if both A and B arrive at the same time. Then it makes sense to run the shortest job first. What if they don't? In that case, what you would want to do is preempt, right? Preempt the thing. So imagine you are the operating system, right? You'd have no idea what jobs are actually going to arrive, but you somehow have figured out what time they're going to take. So A is running, you are here, right? This is a timeline once again. This is a time equal to 0, this is some time. So you are running A, you know it's gonna take this much of time, right? All of this shaded area. And you are currently over here. You have run A till that point. And then there's another job B which could arrive, which you could start doing, right? And B takes slightly shorter time, so it would complete first as compared to A. In this sort of a scenario, you can prove that what you should do, so basically it's like A and B, this part of A and this part of B both arrived at the same, so let's call this thing as A dash and this is B. These arrive at the same time. In that case, it's gonna make sense to run B first for the best turnaround time. And so you'll switch from A to B, and then you'll not run this, but instead delay this thing. And so you'll run it much later, right? You'll run B, so you'll run A somewhere over here. And yes, it does have an overhead for context switching. We are including that as well, but then again, it's much smaller compared to the jobs themselves. So this gives you the best turnaround time, right? Yeah, assuming that context switching takes no time, but okay, it gives you competitive turnaround time is what I should say. So shortest job to completion first, which is also basically the shortest job with preemption, is the algorithm for turnaround time, right? It's provable that this algorithm is optimal. But sometimes we don't just want efficiency, we also want sustainability, right? So if one of these processes is a short one, sure, but what that process is doing is that it constantly making system calls, right? And it's like waiting a lot in that sort of scenario. So you can think of it as like being a bunch of different processes, and it wants, you know, constant responses. In that case, you would want it more to be fair rather than for it to be efficient, right? So like, let's say you have a process A which is all CPU, it does not make any IO operations. That's A, and B both arrive at the same time. B is like this, it first does some CPU part, then it does some IO operation, and then it does once again some CPU part and does some IO operation. So we don't know how much you'll have to wait for the IO operation to return back, so it will go into the wait state a lot, and just keeps doing this. And it just so happens it's actually a pretty long job if you think of all of it combined, right? So according to shortest job to completion first, you should just run A and then go for B. What it is that it's unfair for B because it's not getting the response time that it should get, right? What if this is a routine that is very important for you to have like in that sort of scenario, like you want it to be like, I don't know, maybe it's something related to your monitor screen, right? That you have to constantly update the pixels, otherwise the user won't be able to make sense of what's going on. In that case, you can't just wait for your CPU to finish some computing task for your monitor and graphics to be updated. You will have to do this. You'll have to run B for a while, and then when it does this IO operation thing, it's gonna wait, obviously. So maybe it's like sending a signal and then it's waiting for a signal. So once it sends the signal, you'll switch to A. So while for the time when it's waiting, you'll switch to A, and then you'll start again. So you take in whatever input you got, and then you do this, and so on. So this is a better strategy than just running this first and then running that, because running this over here would have no actual usage, right? Because the user is already frustrated by this point because of how unresponsive the system is. So you want your system to be responsive, so that's why you require response time to be low. So the algorithm which is best for response time is round robin, particularly the round robin case where you have very small time classes. So how does round robin work? You have a bunch of people, so you guess people A, B, C, D, right? And you have a set of items, right? So it's like I1, I2, etc. items, and each of these people have different valuations for the items. What round robin does is that we start with any one of them, right? A, and then it assign A whatever is the highest valued item from the list as per A. Maybe A value is I1 the most. Yeah, sure. So you just assign I1, right? And then you assign B with whatever is the highest valued thing from the remaining list as per B, right? As per B's valuations. Maybe it's like I2 and so on. And so you'll just keep doing this. And then once all the people are done, you'll restart, because if the list is not dead yet, you'll restart and like I1, etc. So this just keeps on happening, right? In this case, the thing that we are assigning to people is a time slice. So you're assigning time to people basically, and each time slice is equally important, and it's same valuation for everyone. Okay, maybe not the same valuation, there could be priorities, but we'll come to that later, but we're assuming it's the same valuation for now. Then what's going to happen is you'll have a slice dt, right? So ABCDR processes, you'll assign dt to A, then dt to B, then dt to C, dt to, this is by the way your time, and then once again you'll assign dt to A, dt to B, and so on. So this will just keep on going. And so what's happening is you're running these in a circular fashion, and the reason that you are doing this compared to anything else is because of the priorities. Alright, now if there were priorities, then you would have different time slices, right? So like if B does not value this time slice as much as, how do I even say this thing, I don't know. Basically in that sort of scenario, when you, okay, let's actually not even think of how do I say this, okay, whatever, just gonna move on. So this is basically round robin, right? Now what could happen is, the problem with round robin is that it does not actually take into account the fact that turnaround time is also a factor. So you want some sort of a mesh of these algorithms which take both into account, and that's where the multi-level feedback queue comes in. So what this thing does is, once again, it has a time slice, right? So it has a bunch of levels, so it's going to be like level 3, level 2, level 1, level 0. So these are basically like priorities for different processes. So if your process is at a level 3 and it's assigned a time slice for it to do something and then give up the CPU, right, make a system call, it doesn't do that, it just keeps on running. Then what the OS will do is it will degrade this a level, it will make it level 2, right? And what's going to happen is all the higher priority tasks will be the one that CPU will want to do. So CPU will just keep doing its high priority tasks until all of them are done, and then the low priority tasks are the one which will get a chance. So here's a real-time thing. So let's say you have three processes A, B, and C. All three of them are level 1, right? So these are like this is a linked list that you have. This is a Sential node. This is a linked list that you have. Now what happens is you start running A. A takes too long, so you kill it. Okay, you don't kill it, but you preempt it. Then you'll have this structure, and then it's like this. Okay, so now you have context switched to B because it's the next one in the level. B is okay, it doesn't take too long, it gives up the IO, right? Then you go to C. C takes too long, you go like this, you go back to B and back to B and back to B. B completes, B is done, there's nothing in this thing, this is an empty list, so this is a null pointer. All right, empty list. You go to A doesn't take too long, right? So every level has a different time slice allocated to it. So this would have some dt1, so dt3, this has dt2, whatever time slice, and so A doesn't take too long in this level, and so it's okay. So like, okay, in that case we'll keep doing it. It's given up the CPU now. Okay, we'll context switch to the next thing. So C is what you run, and then it doesn't take too long. Okay, you go back to A, it takes too long, but at this point it's also very close to run to finishing. So you preempt this, you go to C, and this goes to A, and it turns out that C is a malicious process, that it's constantly just making IO operations, and that's why it's getting high priority. So like it keeps making IO operations, that's the problem. But yeah, so C just keeps on doing, and at some point it runs completely. I don't know what happens, but it runs completely. So then C is done, so it's just a null pointer over here, and then you go to A, and then you complete A, and then it's a null pointer. So that's how multi-level feedback queue works. You can obviously see the problem with this thing. The problem is that whatever are the lower level jobs, they won't ever get a chance to run again until the higher level jobs are completely done. This is a problem of starvation, right? Your lower level programs starve, and these could be important computations. It's just that they're not doing IO operations, and because of that, they're starving. So what if like there's a read after write problem? Well, okay, if that's the case, then you will probably do a lock and sort of checking and all of those things, but the programmer isn't wise enough, right? In that case, you want these CPU intensive tasks to complete. So what you'll do is that periodically, let's say at some t period, you'll bump up all of the jobs to the topmost level. Yeah, that's what you'll do, so that everyone gets once again a chance to compete. This also solves the problem of a process having a changing behavior. Like at some point it does like a lot of IO operations, and then at some point it does a lot of CPU operations, and so it's problematic what's going on the process. You cannot judge the process, right? So you want it to constantly change in your priority based on how it's performing. So, and that's why you keep doing this, you keep putting it up. You obviously have different time slices. Here's another thing which is also important. If some process is malicious, it would just have a lot of timer interrupts, right? Just like, sorry, not a timer interrupt, a lot of IO operations, which is just doing in vain, right? It's just like putting things to the null file or whatever. It's just doing that constantly. In that sort of scenario, what you want to do is you want to allocate a fixed amount of time. It's not a time slice, it's much bigger than a time slice, but you allocate that time to a process at a particular level, and if it exceeds that, right, and it could exceed that in many turns, right? So all of that summed, if it's exceeding the time, then you'll just switch to some other process, right? Because so as long as it's high priority, things are going to be a problem, right? You don't want it to be high priority all the way. So what you can do is like you do this and then you switch to some other process straight up, like after this much of time has passed. This allows important things like the task managers and security checkers to actually run in the background, even if they're running slow, so that you can identify that this process is malicious, and then you can end the process. And yeah, so this is the only algorithm so far that we have discussed that is actually practically implementable, because this does not require you to know the runtimes beforehand. All of these other algorithms, they do require you to know that. And yeah, so there are also some other algorithms which people tend to use. One is called the lottery system, and the other is called strike scheduling. So lottery system is basically just say this. It's the same as the multi-level feedback queue. You still have priorities and all of that, except it's not exactly about priorities. It's like probabilities, right? So how likely are you to be the next process after a timer interrupt is based on the number of tickets or lottery tickets that you have. So what happens is every process is given a bunch of tickets, and then based on how many tickets they have, you have the probability of them being run the next day. So processes can share their tickets within their families. When I say families, I mean child processes. You can share those. So like if you have two applications A and B, you want both of them to be given kind of the same priority, even if A actually has a lot more threads or processes inside of it, because in the end there is two applications, right? So that's why the ticketing system works. Yeah. Now obviously you need to actually assign these lottery tickets to people, right? And so the way to do that is well, it depends. It's a design choice. Yeah. So there are schemes which update these number of tickets that you have, but this is a good algorithm because it's probabilistic, because of this randomness, you never have the problem of starvation, because probabilistically speaking, like at some point you will have some low level process running, right? At some point you will. But there's also the problem of uncertainty, that whether or not that will actually happen soon enough so that the user does not get frustrated and just like kill the system right away. So to help with that, there's another modification which is called as stride scheduling. This is more of a deterministic algorithm. It does not rely on lotteries. Instead, it relies on like how much has the process been completed, and just how much is speculative. It's not actually like you don't know the runtimes beforehand once again. So instead what it does is, based on the priority, it gives each process a stride, right? So a stride is like the percentage of progress that it will make every time slice. So every time you have a timer interrupt go on, your pass value, which is like how much of the process is done, is incremented. So the processes which have the lowest pass value are the ones which are favored, and they are run. So this ensures fairness in a very deterministic manner, that every process, like you have process A, B, C, so you learn their strides as time goes on, and you make sure that their pass values are, so this is like total amount of time that you will require for each process. You ensure that their pass values are kind of similar, right? So this is the shaded area is how much of the process has been done so far. The disadvantage is, like if we have a new process E that just arrives, it's problematic because it has 0 as its pass value. So until this like level is reached, you are only going to run E. You won't even touch A, B, C or D, which is a problem. It's kind of a problem. So it's more or less impractical, but at least it's deterministic, so you don't run into the uncertainty problem with the lottery system. So finally, there's also something known as the completely fair scheduler, which is something that Linux distros use, and it's too complicated. It uses these balancing trees, red, black AVL trees, and it accomplishes a lot of things. It gives great turnaround times. At the same time, it also gives fairness by deterministic algorithms. So go look for that. Like I was advised to not read on that just yet because it's not going to the quiz, but yeah, go look at that if you want. Now next, this is not important. This isn't important yet because we haven't reached address management yet. So I'm just gonna go over whatever happened in the last few lectures. So this was in the January month. So for 15 days I haven't been going to lectures, which is a shame, but I guess I can read from the slides. So okay, so January 20, the problems with MLFQ naive algorithms. Well, I'm just gonna list some of them down. 1, starvation. It's a big problem. Lower level things starve. Second, changing nature is not accounted for. Third, malicious processes. Like if you have antivirus and you're not allowing the antivirus to work because the virus process is just calling up a fuck ton of IO operations, your OS sucks basically, right? You're not even allowing a simple thing called an antivirus to work. So malicious processes can easily game the system, and that's a problem, right? Yeah, you could literally have a process which just, which just extract all the information, all the security problems, like all the information that you have in your system, and it does it only by calling a bunch of IO operations constantly, right? Like you're not able to check what files this thing is handling and what's going on. Your antivirus is shit because it's just not getting a chance to run. Like no matter how sophisticated of an antivirus you built up, if a malicious process just keeps on calling the IO operations, well, you're not gonna ever be able to run this. So that's a problem. You want all operations to be making some progress at least. So that's 3 problems at least: starvation, gaming of the system, and change in the nature of the program, right? So most of the actual OS, they used CFS. There's also something known as BFS. It's not the breadth first search. It's messed up naming. I don't know why they named it that, but yeah, you can also search that. So for multiple CPUs, each CPU has its own cache. Yes. And this is something that we have to be wary about. So whenever you context switch, the other process, its cache is not actually stored anywhere. So it has to run for long enough for the cache to become usable again. When I say usable, I mean the locality of the stored data, it should be there, right? So you have to run it for a long amount of time for the cache to be extremely useful, but you won't allow it to be running for a long amount of time because obviously OS it like comes in and does a lot of other things, right? And so what a lot of time happens is that your cache is just big enough that multiple processes can run at the same time in your cache, right? That this is your cache. I'm calling it cache. I don't know the correct pronunciation of this thing, but so what should happen is like process A should only use this part of it, process B only uses this part of it, etc. This is what should happen ideally. Cache should be big enough for this to happen. So when we say cache affinity, if this is like at CPU 1, so every CPU has its own cache, right? It's just like one big hardware support thing, right? So like this is your processor, this is your L1 cache, L2 cache, this is your L3 cache, which is like the L0 cache is obviously like the register file. So this is like the main memory, right? Sorry, the primary memory. Yeah. So context switching from one processor which you have a cache built up for to something else which does not have it, it's a bad idea because your average memory access time, it dramatically increases for a short while. So this is the problem of cache affinity. So a process that started running on a CPU A should keep running on CPU A all the time so that you can use the cache data, right? So having a single queue, let's say you're just running a simple FIFO algorithm for multiple CPUs, having a single queue is a problem. Instead, for every CPU you should have a queue. So it could also be a priority queue, like a level feedback queue. Doesn't really matter. It might just be a priority queue, like so you can figure out the shortest job first. But yeah, it could also be a multi-level feedback queue with a bit more complications, but whatever. So in a system like that, each of the CPU requires its own queue. All right. Yeah. All right. Hey, even the multi-level feedback queue is just a queue in the end. Like it's a priority queue because it tells you which thing to run the next based on what priorities. So like a simple queue just has priorities so you can think of it as a mean as a priority queue as well, because it's just like the priorities based on the order of arrival. FIFO, right? Last in, last out, first in, first out, whatever. The priority queue is just like changing the priorities based on some other thing, etc. Yeah. So even a multi-level feedback queue is just a priority queue. You can think of it like that at least. So using a FIFO with a single queue for multiple processes, so multiple processors is bad because we don't have cache affinity at that point. So we do want to have different queues for every processor. The scalability of multiple queues, processors work as if they were the only CPUs. So our processing capability actually scales up proportionally, right? So here's the problem. With a single queue, right, you have this problem of like, one thread going into the other. It's like, I don't know how to say this thing. The process is constantly being in different processors all the time, and so what ends up happening is that like a CPU is running a bunch of processes which it has never seen before, and because it has never seen before, it has never built up the cache for that. You do not want that. You don't want that to happen. You want processes to run a bunch of processes as if those are the only processes to exist, and it does not know anything other than that, right? So it's like your CPU are employees. You want your employees to focus on only the tasks that were assigned to them and not on the tasks that other people are doing. So the only time that you allow that to happen is when one of the people has very little tasks, and so in that case they will steal tasks from other employees. right? So when a process is migrated from one queue to another, the cache is copied as well. So whatever notes the other people are making for that, think of notes as the cache. So those things would also be copied from them to this employee, right? So whatever the work other people did, you are just stealing all of the work, right? So processor with less workload steals. Normally you don't want that to happen because copying this cache thing also takes time. So you don't want the processors to steal workload, so you want them to be fairly assigned, like equal kind of workload to everyone, so that this weird stuff does not happen. But it's okay, like even if it's stealing, it's doing it by using its own processing capability, right? So other processes are not really like getting affected by it, so it's fine. It's not doing harm, right? That worker isn't really doing harm, but it's not it's also not doing the thing as effectively as it could if it was already assigned those tasks beforehand and didn't have to steal those tasks, right? Yeah. All right, now we have this thing, I think. This is just basic stuff about virtual memory. So you have a base and bound algorithm. So upon a fork, a copy of the address space is created. So the address space is usually managed using base and bound registers, which are once again stored either in the process struct directly, they have hardware support for them, etc, etc. So usually processors can only share secondary memory, because once again disk operations, like those aren't exactly addresses that you can just reach. I mean, they are, okay, come on, they are. You have an IO port and then you have the address in that, sure, but usually processors do not have virtualization and privatization of those things. They still share the secondary memory. All right, so shared memory segment is a segment in the RAM that is shared by multiple processes. Processors can also communicate with message. So this is an important thing. This is something that we'll learn about in logs. So you have things called message passing, which let's say a producer process and a consumer process can utilize, right? So producer consumer problem is basically a producer process is writing at some memory segment, let's call it the buffer, just I don't know, some address that you have, and let's say it's in RAM, right? It's writing in RAM, and the consumer is using that to do something else. So this is actually like threads, right? So producer consumer like threads and they're doing this, but it could also be processes, and then you just have to change from RAM to secondary memory and it still works out perfect. So yeah, you literally have like locks for all of these different devices. So come on, it's fine. Just even if you're thinking of it at thread level, it's okay. So just say everything is in RAM, producer consumer are two threads, same virtual address space. The producer is trying to write to a buffer, consumer is trying to use that buffer. What we want to happen is that the consumer should only be able to use once the producer has written, and the producer should also be able to write only when the buffer is empty, as in the consumer has used it. So there could be multiple producers and there could be multiple consumers. This is the classic producer consumer problem, and it's also called a race condition, because what you want is your consumer shouldn't be like, your consumer should not arrive too soon, right? But also not too late, such that the producer already like done two repetitions. That's like, then you have lost data. So you have to make sure it's turn by turn, right? And you don't have like two turns to the same person consecutively. So compilers can do reordering of assembly instructions to reduce stalls in pipeline. Okay, this was unrelated. Why did I write this after this? Oh, okay, because they're introducing logs, right? So producer consumer problem is one thing which is solved by logs. Next thing that is also solved is weird reordering of instructions. So if anybody of you have taken a computer architecture course, you would know that compilers do the static reordering of assembly level instructions so that it runs better on a pipeline processor. So this reordering can be really bad for us at times, because remember, we want some instructions to be atomic, and if the compiler does not see them as atomic instructions, as just instructions, it's going to reorder them, and then some weird things will happen. Right? And that's where the part of volatile memory accesses and critical section comes in. So volatile memory access is basically like when the processor sees that a a variable is being assigned some value, but then it's never used. Like, what was the point of assigning it? So it like thinks smartly in quotations, and then it just deletes the assignment completely. I don't know who made it like that. That it doesn't listen to the programmer; it listens to its own thinking. I don't know. It's just stupid, but so it thinks that it knows better than the programmer, and it just deletes stuff as per its whim. So you have to literally do some compiler directive things, like disable this optimization. It's not even optimization, so that the compiler actually starts working as a sane person. But yeah, so there's this problem that we want to solve with critical sections. So this is all about locks. So here's a very toned down version of the problem. Suppose there's a unit X and you have two threads. Both the threads can run this unit X. So unit X is just a bunch of instructions, okay? But you don't want so there are threads A and B. You don't want thread B to be running the instruction while thread A is also running the instructions. And A should also not run X while B is running. So what can you do? What can you do to make sure that A and B do not ever have an overlap, right? They did not run the critical section simultaneously. Well, introduce locks, right? So one basic strategy would just be like, what A could do. So let's say you like are two people and you live together, and you have a shortage of milk, right? And so what happens? And you can't communicate. You people are like I don't know, very bad relationship that you have. Okay, so one of you sees that it's like the fridge is empty, there's no milk, and you want that person goes to the supermarket and then buys milk and comes back, and he sees even you did the same thing. So now you have two bottles of milk or two crates of milk when you should have ideally only had one, because you know that the other one is going to be like rotten in a few days. So how do you avoid a situation like this when both of you basically like saw the opportunity to buy milk and both of you went and bought it, but now it's like wastage of money and time and resource? So in such a scenario, one basic thing is to leave a note, right? So before you close the fridge, you are going to leave a note that I'm going to buy milk, and when another person sees, they'll be like, okay, they are going to buy milk, so I should not go to buy milk. And there you go, problem solved. Now there's a problem with this thing, right? Yeah, what's the problem? Hey, okay, I kind of forgot what the problem was. Oh yeah, right, okay. So this isn't exactly how it works with CPUs, unfortunately. In CPU, so a person, what they can do is that they can actually see what's going on. Like, they can see that there's a note, and then they won't put their note on the fridge, and like they'll just stop the process, right? But that's not how actually CPU works. CPUs are pretty dumb. So what they'll do is, you leave a note A, right? A does that. B also does that. He leaves a note B. Even though like he could literally see that A has left a note, he'll still leave that. Next, he'll check if A has left a note, and he has left a note. So he won't go for X, and then he'll just remove it. Sure. And I imagine if A is also doing the same, that he checks that. So it's a bit of an interruption. Okay, there's a bit of an interruption. Okay, I'm gonna pause for now because there's an interruption. I'll be back